Dark Matter and Dark Energy by Brittany Thompson. In the last 2 decades, scientists have discovered that only 4.4% of the universe is visible matter. A dark form of matter is the central source of gravity. Fundamentally, it is different from stars and galaxies and the atoms that make up everything on Earth. There seems to be a dark form of energy which is driving the expansion and counteracts gravity. Dark matter's existence is not visible to the human eye because it emits little to no light. However, it has a strong enough gravitational influence on its surroundings that supports its existence. Surprisingly, dark matter makes up for 23% of the universe. Scientists have divided dark matter into 2 different options. The first option is ordinary dark matter, found in very dim objects. It is made up of protons and neutrons, etc. Dead or failed stars in the halos of galaxies have been nicknamed massive compact halo objects, or MACHOs. Despite there not being enough to explain dark matter, it has been observed through lensing that these MACHO stars make other stars appear brighter. Opposite of ordinary dark matter, it is not made up of any form of normal matter. Extraordinary dark matter consists of unknown neutrino-like particles, which are called weakly interacting massive particles, or WIMPs. There is simply not enough ordinary matter, which is why scientists believe WIMPs to be a form of dark matter. Dark energy is also unknown and seems to be the cause of the expansion of the universe accelerating. Additionally, dark energy makes up 73% of the universe. Using the orbits of planets, scientists are able to measure the mass of the solar system. Using the orbital period and average distance, then for circles, orbital velocity and orbital radius. To measure mass, scientists use a graph to show the rotational curve of galaxies. The rotation curve is a plot of orbital velocity versus radius in the disk of a galaxy. In the solar system, the sun holds nearly all of the mass. So since the mass is concentrated in the center of the galaxy, the velocity decreases with the square root of the radius. This behavior is known as Keplerian decline. Scientists expected the rotational curve to decline when they were measuring the mass of the Milky Way along with other spiral galaxies, but the rotational curve remained flat, disproving their theories. This means that mass is more spread out in the solar system than originally estimated. Unlike stars, the mass in the Milky Way does not glow and is extended in a large region. Most of the mass seems to be dark matter. To measure the rotational curves of other spiral galaxies, scientists use the Doppler shift with hydrogen gas. This shows they all tend to have flat rotation curves as well, which also indicates extreme amounts of dark matter in all of them. Broadening of spectral lines in elliptical galaxies show scientists how quickly the stars are orbiting. There are about 10 times the amount of dark matter in stars in these galaxies. There are 3 methods of measuring cluster mass, and they all seem to show the same amount of dark matter. The first method uses their Doppler shifts. The second method measures how galaxy clusters have large amounts of X-ray emitting gas. To get the cluster mass, they use the temperature of hot gas, which is 85% dark matter, 13% hot gas, and 2% stars. The third method is gravitational lensing, which is the bending of light rays by gravity. This brings out more evidence for dark matter because it reveals much more mass than we can see. Scientists either think that dark matter really exists and we are correctly assuming its effects on the universe, or if we are wrong about dark matter, then we have to be mistaken with our understanding of gravity. Since gravity is very well tested, they believe that they are under the correct assumption. They also believe that without dark matter, some observations don't make sense. Dark matter seems to be pulling things together, which is shown by galaxies moving towards the densest regions of space. This is also where the dark matter is most dense. The universe started out smooth, but as a result of the dark matter, it grows lumpier with time. Also, the gravity of dark matter seems to be what drew gas together into progalactic clouds, initiating the process of galaxy formation. Characterization of matter and light visible on the largest scale, which is larger than any galaxy, is called the large-scale structure. It shows superclusters and voids on a scale of millions of light years. Dark matter is the only thing that can stop the universe from expanding. But there is not enough dark matter to stop the universe, and it appears to be speeding up. Since this is happening, there is something working against gravity. This could be dark energy. Scientists use white dwarf supernovas as standard candles by measuring how their brightness changed over time. This was observed to show the history of the expansion of the universe. It was expected that the expansion would be slowing, but the supernova was fainter than they thought, which means the expansion of the universe was accelerating. This white dwarf supernova are evidence for dark energy. Another piece of evidence for dark energy is Einstein's cosmological constant. He introduced this constant into his general relativity when he saw his theory was predicting an expanding universe. Then, when Edwin Hubble discovered the expansion of the universe, he dismissed his constant. It then later became identified with what quantum theory calls the theory of the vacuum. To conclude, dark matter and dark energy leave lots of room for exploration, but there is a lot known about it.